Hi, everyone. Welcome to this video in which we'll be talking about simulations, basics of simulations. Specifically, I'll be talking about how you simulate discrete, uniform, and normal distributions, random variables that follow these distributions using Excel. That's uh, uh, that's what we're going to be doing in this video, right? So to motivate this, we'll look at a simple example. This is from the textbook. It's an example called the Santronics problem. So Santronics is a startup company that manufactures medical devices for use in hospital clinics. This is a new device that has the potential to capture a large share of the market. And what Santronics would like to do is analyze the first year potential for this device, right? Given the tight cash flow situation they are concerned about the potential for a loss. Now, the key parameters that they are considering for this high level simulation is the sales price per unit, which is P, the first year administrative and advertising costs, which is CA. These are fixed costs, they don't depend upon the number of units you produce. Then direct labor and parts costs, which are both variable costs, which are per unit. And finally, demand, which is D. Now, after conducting market research and financial analysis, Santronics estimates that the device's selling price will be $249 per unit, and the first year administrative costs, all the administrative costs put together, will be about $1 million for the first year. So this includes all the people you need and all the advertising costs and all of that, all the administrative stuff, right? Now, Santronics is not certain about how much the labor cost is going to be and what the parts costs are going to be. So they are variable, and they also don't know, obviously, don't know what the demand is going to be in the first year. Now, if you set this a problem up, this is a simple problem of calculating profit. Profit will be the price per unit minus the variable cost values times demand minus the fixed cost value. So that's the total profit. And as far as you know, the values that we know are we are selling it for $249 per unit, and that the fixed cost is going to be $1 million. Now, the whenever you do simulation, there's always a base case scenario. This is the scenario where you assume specific value for parameters that are usually uncertain. In this case, we are assuming that labor cost is about $45, parts costs are $90, and demand is going to be 15,000 units. This is the base case. For the base case, our profit will be $710,000. But this is obviously not going to be the exact scenario that they face in the first year. Now, they might potentially be able to fix the labor costs and the parts costs, but demand, they definitely cannot estimate exactly what the demand is going to be. Demand is going to be variable one way or the other. But in this problem, the assumption is that the parts costs and the labor costs are also going to be variable, right? So, for those 3 points of uncertainty, this is what Santronics is assuming. Santronics decides to describe the uncertainty in parts cost with a uniform probability distribution. That is, you're saying that cost per unit can be anywhere between $80 and $100, and the probability of being between $80 and $100 is equally likely. So it can be any number between $80 and $100. So that is a uniform probability distribution, right? The demand for the first year, they are assuming it follows a normal probability distribution with a mean of 15,000 and a standard deviation of 4,500. So that's the assumption for demand. So demand will follow a normal distribution. And finally, um, the labor cost they are going to assume follows a discrete probability distribution, which takes these particular values. So labor cost can be either 43, 44, 45, 46, or 47, one of these five values only. It cannot be 43 and a half or 45.25 or any of the other numbers. It can only be one of these five values with these probabilities. So that's the probability distribution for labor costs. So these are the three different types of probability distributions that I want you to be able to simulate, and that I'm showing you how to simulate in this particular video. And yeah, so this is an example where we use all three. So we have a discrete distribution, we have a uniform distribution, and we have a normal distribution, right? So how does the simulation process work in general, right? Now, before I proceed to that, proceed that, once you know how to simulate these values for this particular example, you just use the same idea wherever you see these simulations. But to do that, you need to know what the simulation process is like. So to simulate the Sandtronics problem, we must generate values for all three of these random variables. So the three random variables are the labor cost, the parts cost, and demand. Those are the three random variables, numbers for which we don't know what the values are. So set of values for a random variables is called a trial. So in a single trial, you'll generate one value for each. Then we'll generate a second trial, then calculate a second value of profit, and so on. So we're going to do this multiple times. So we continue this process until we are satisfied that sufficient trials have been conducted. So there really is no mathematical way of saying, hey, you need 50 simulations or 100 simulations. That comes down to how much you can do. Sometimes simulations can take a very long time, so you can only do so many simulations. But if simulations are very cheap, you might want to do as many as you can. So there is always the back and forth there, right? Now, the other part of the simulation process is the simulations itself. So usually what we do is we generate random numbers, and whenever you use computers to generate random numbers, they generate random numbers between 0 and 1. So all values between 0 and 1 will be equally likely. So it is basically a uniform distribution over 0, 1. Now mostly you will never be able to generate one. In very, very, very rare cases, you might be able to generate 0, but even that, the probability is very, very, very low. So it's almost close to 0. It will be all numbers between 0 and 1. And in Excel, the way you do that is by using the RAND formula. So RAND formula will be the basis for all the simulations that we do, right? So let's begin. So let's begin with the discrete random variable first. So for the discrete random variable, we will use I'm sorry. So this is how we do it. So for this is the discrete distribution. So this is the direct labor cost per unit. So it can take the values 43, 44, 45, 46, or 47 with probabilities 0.1, 0.2, 0.4, 0.2, 0.1. Another thing about the probability distributions obviously is that the probabilities all have to add up to 1. Otherwise, you're not describing all possibilities. So what we do is we take these numbers between 0 and 1 that we generate, right? And then we divide all numbers between 0 and 1 into intervals. Intervals between 0 and 0.1, then 0.1 to 0.3, then 0.3 to 0.7, 0.7 to 0.9, then 0.9 to 1. And the way we do it is that the length of these intervals is exactly equal to the probability. So between 0 and 0.1, the length is 0.1. 0.1 to 0.3, the length of the range is 0.2. 0.3 to 0.7, the range is 0.4. 0.7 to 0.9, range is 0.2, and 0.9 to 1, the range is 0.1, right? So you have to divide up the interval between 0 and 1 into these sub-intervals. Now, the reason why we are doing this is, remember, we are going to generate all random numbers. The first thing that we always do is generate a random number between 0 and 1 using the formula equal to rand. So by generating this number, we'll get a number between 0 and 1. Now, because we are randomly generating these numbers, they can represent the randomness in real life. So if you randomly generate a number between 0 and 1, let's say we generate a number 0.4756 or something like that, right? So if we generate a number 0.4756, then we come look at these intervals and say, hey, 0.4756 lies in this range. So for this particular trial, my value for direct labor cost will be $45. If I generate a number 0.9999, then for this particular trial, my direct labor cost will be 47 because 0.9999 lies in this range. So any number that you generate between 0 and 1 will be in one of these ranges, and the probability that it is in one of these ranges is exactly equal to the probability values that you have in the distribution itself, right? So that's the idea for a discrete random variable. For a uniform random variable, the way we do it is you generate the value for a random variable by using this formula, which is you use the lower limit plus the difference between upper limit and lower limit, which is the range of numbers that you have, times the random number that you generate using the rand formula, right? So for example, in this example of $80 to $100, the parts cost will be lower limit, which is $80 plus the difference between the lower and upper limit, 80 and 100, so that's 20, times the random number between 0 and 1 that you generate. So that's the formula for the parts cost. And finally, the formula for to generate a normal random variable, the formula that we use is a norm.inv. So this is the inverse of the normal distribution. And there, the first value that you use, this is the probability value. This is the random number that you generate. So you randomly generate a probability value. Then the mean and the standard deviation for the distribution that you are, the normal distribution that's associated with the random variable. So in this Santonic problem, the first year demand is normally distributed with a mean of 15,000, standard deviation of 4,500. So the demand will be simulated as norm.inv. Random number will be the first thing, and then 15,000 for mean and 4,500 for standard deviation. Right. In the next video, I will go over how you do this, how you simulate this in Excel specifically, and we'll look at some of the results that you get out of that. So this is already longer than 10 minutes, so I'm gonna do this in the next video, right? Take care.